and quantum information.
So my topic was the superposition of wave functions in a harmonic oscillator. So to get a couple of things defined first, cat state is a superposition of wave functions, and it's defined with opposite and equal momentum, not necessarily equal, but usually equal momentum in a closed system. So to create a cat state, you just set up two wave functions. In this case, it was in a harmonic oscillator, and they would be about the same distance from the center apart and have equal and opposite momentum, so they would crash into each other. And then using some of this, we can put different coefficients in front of the two wave functions in order to create different cat states and demonstrate a block.
Why cat? It's not bra and cat, it's something different.
The cat is for Schrodinger's cat. It was named after that because they said they have two distinct and opposite states, life and death. And so since they have two distinct and opposite states, cat state. I didn't name it. So a little bit more background. So
Schrödinger was killing cats?
Yeah, trying to. And a qubit, a little bit more background. So this is getting into more like the quantum computing and quantum information. So a qubit is a basic unit of information in quantum computing. Much like a bit in regular computing, a bit can only have 0 and 1, whereas a qubit can have any of the values in between. And it does this by having a cat state, or just a superposition of states. So a major challenge right now is actually how to read a cat state, because as you'll see in my or how to read a qubit. So as you'll see in my presentation later, there's a visualization of when the two wave packets collide with each other, and they don't necessarily have a good way of reading that in real life and to use quantum computing more. So this is, I mentioned a Bloch sphere, and this is a Bloch, is it Bloch? Bloch sphere. The two functions right here are 0 and 1. So this represents a 0 in a regular bit information, and this represents 1. So if you only had 1, like if you were in the bit, you'd only be able to either be at this point or this point. But with a qubit, you can be at any point on the surface of the sphere.
Alex, what is regular bit without Q?
It's used in regular computing that either you can have 0 or 1, and a bit is used to make up a bunch of different characters, but it only has the power to do 256 characters, the alphabet, and
byte.
some. Yeah.
Byte.
So a bit makes up a byte, which makes up more and more and more. And you can have computers right now oftentimes you'll hear the term 64-bit. That uses 64 bits in one processing unit. So continuing. So my experiment was to set up two different wave functions that, like I said, that had equal and opposite momentum. So this is the two wave functions represented. For those of you in this course, you probably recognize the little bit of wave functions because they're what we used in the original harmonic oscillator. There's some slight differences here, where this is the initial momentum of each of them. This P1 actually could be represented with a negative P0 if you so decided, but in order to make it a little more obvious, and as well as these two represent the initial positions of the wave functions. So what we did was we set that up and we let it run. In order to get them to crash into each other, however, we needed to set up an equation that had both of them in it. And these different coefficients out front are the coefficients I talked about. So by varying these, you can get different points on this block.
So your initial state is adding together two Gaussian humps. It's like a camel with two humps.
Yeah,
okay.
So it's a camel cat state. So by changing these two coefficients, you can move this point all the way around this Bloch sphere. And in order to get the expected outcome of where these are, there's equations can be derived. It's a little bit long on how to get to these, but you can use the coefficients of 0 and 1 in order to determine where on the x-axis and where on the z-axis it is. In this experiment specifically, did I have it? No, I don't have it on the next slide. I don't have it on that slide. we decided to say that we were going to have y equal to 0, and you can do this if you, because on the sphere we automatically assume that c squared plus c0 squared plus c1 squared equals 1 in order to give the radius of the sphere. And then if you set one of them arbitrarily, one of the imaginary parts of the coefficients equal to 0, which you can assume based on this equation, you can only get half circle, because you can't go into the negative because that's imaginary for the y portion. And you can only stay in the positive. And I'll have a visualization of this later, and it'll be easier to explain. So keep going. So this is just some code from the actual experiment. So this is all the initial variables that you had to set up. Normally, for some other people, they only had p0 and x0, so they only had one wave function, but in order to set it up, you just had to add a second wave function and a second initial position. The middle was set to be 40. And then, in order to go through this, you just set up the same wave function, just with different variables, as you can note throughout the code. And something that I forgot to do when I originally made it was I forgot to actually add them together, so my code was getting a major error, and I was wondering why it was doing that. But you had to add it together. And in order to get the system to have the coefficients, I named the coefficients AGQ1 because I didn't know what variables were actually taken. I didn't want to look through the long list, so I just kind of hit my hand on the keyboard, and that's what came out. And so I also thought theta was taken, so I just changed that a little bit. And in order to change it, you just change the number in front of theta, in front of pi, in order to get a different theta, so that your sine and cosine will change the coefficients in front of it just slightly. So you can read that, but we'll get more onto the visualization since it's easier to explain. So like I said before, instead of having a sphere, we only had a half circle. So this is 0 and this is 1. And then these are different coefficients multiplied by pi. And so if you actually wanted to, and you included the imaginary units, if you went back to 0.375 pi, it would just keep going back around the circle. But note, since we're only dealing with one coefficient having imaginary units, we only had to deal with one part of the circle. Oh, pi got deleted there. Uh-oh. But by changing the theta, and this is like 3/4 over pi, half pi, regular pi, you get to have different coefficients. And this is a nice big old table to explain all of that, of course. And then using that, we can determine Sx and Sz is cut off here. But Sz will show that at this position, it'll be +1, and Sz at this position will be -1, and x will equal to 0. So now when you're actually in the wave function, when you watch them crash together, you can see the different wave functions as the probability as they go through time. So as you can see, they'll start over here and kind of go throughout. And then the C is the middle position. So you can see when they get to the middle, they crash together. And in a sec, you'll see the standing wave that they actually create. So when they come together, they create that cool little standing wave. And this right here, when they come together in the middle, is where they sometimes have trouble in reading the qubit, because when they have two different superpositions like that, it's hard for current computing techniques in order to quantify this. And so this is where people are having a lot of research trying to find information about this. Because once you have a qubit, once you can read a qubit, their computing increases by, I think it was 10,000%. So I mean, it would be very useful to have that, obviously. And so this is more of a superposition, like in the middle of like a quadrant of the sphere. So as you can see, 1 is obviously much bigger, representing that it's closer to the bottom or the top. In this case, it was actually closer to the bottom. And if I let it run, you'll see it collide once more. But then if you take out one of them completely, it just goes up and down as a normal harmonic oscillator would. And I believe that is the end.
Okay, but thanks, Alex. So any questions about his presentation. No questions. How do you create them? How does experimental setups create these superpositional states?
If I go back to the code.
Not in your modeling, but in wet chemistry or in like hard physics.
You would have to create two different bits, and bits are just an alternating of currents. So 0 is one current, and 1 is a different current. And in order to create this, you have to have two different ones. You don't actually have to have two different ones, but most of the time you have two different bits. And then in order to read it, you have both of them in the middle, and you're trying to read in between them. Because when you go from 0 to 1, the change isn't instantaneous. You can't change to 0 current to 1 current instantly. So in the middle is where they're trying to figure out how to get the qubit quantified.
Okay. Let's think about as a group and maybe try to answer this question once again after presentation by Isaiah. He may not know, but his presentation is somehow related to this procedure.